So in our next unit, we're going to look at what are known as zero knowledge proofs. Um, Before we kind of get into the details of that, we talk a little bit more about calculating square roots modulo n. Okay? I think this might have actually come up in one of our class problem sessions, so this may be a little bit of a review. Um, but so remember, if n is equal to pq and p and q are distinct dot primes, and if y is a quadratic residue mod n, then it'll be a quadratic residue mod n if and only if it's a quadratic residue mod each of those primes. And then moreover, we saw that a quadratic residue mod of product of two primes could be recombined to have four square roots modulo n. Um, right, so y is congruent to x squared mod p, y is congruent to z squared mod q. We get two solutions for x, two solutions for z, and then using the CRT, we can recombine those into four solutions mod n. And so this is the bit that I don't think we talked about in the lectures, but how do we actually calculate square roots mod a particular prime? Okay, so it turns out that if a prime is congruent to 3 mod 4, then there's a nice, easy procedure for calculating square roots of a quadratic residue. If our prime is not congruent to 3 mod 4, then it's a little bit more complicated. And we actually won't need that other algorithm because we can just always set things up so we're working mod primes that are congruent to 3 mod 4. Okay. So if P is a prime such that P is congruent to 3 mod 4, and y is a quadratic residue mod P, then minus y is not. Okay, and so that's telling us that since we know exactly half of the elements in Z mod P star are quadratic residues, then actually we're always going to have exactly one of x, and minus x is going to be a quadratic residue. Okay. All right, and this is actually pretty easy to show. Okay, so prove this, and well, suppose y is a QR, then we just apply Euler's criterion. And so y to the p minus 1 over 2 is congruent to 1 mod p. Okay, but then let's apply Euler's criterion to minus y. Okay, but that's minus 1 to the p minus 1 over 2 times y to the p minus 1 over 2. Okay. But this is 1 by assumption, so we just need to figure out what minus 1 to the p minus 1 over 2 is. But my prime is congruent to 3 mod 4. Okay. So that means this is 4k plus 3 for some integer k. Okay, let's think it's just 1. All right, and then if I simplify that, so it's minus 1 to the 2k plus 1. Okay, so it's minus 1 to an odd number, which is minus 1. Right, and so that's telling me then that minus y is a QNR by Euler's criterion. Okay, so just kind of a nice, simple application of Euler's criterion. Okay, so that's good to know. So if we're working on a prime of this form, then if you look at a number and its additive inverse, exactly one of those things will be a QR. All right, now P is congruent to 3 mod 4, and Q and Y is a quadratic residue. So if we let X be congruent, so Y to the P plus 1 over 4, then Y is actually a square root of X. Rather, X is a square root of Y. Again, this is just kind of a matter of plugging in and verifying here, so nothing too complicated. Okay. So what do? I just square x, right? Okay, notice that p being congruent to 3 mod 4 is exactly what lets me know that this exponent is an integer. Just square it. So we get p plus 1 over 2. But p plus 1 over 2 I can write as p minus 1 over 2 plus another 1. Okay, so I can just factor that. Okay, but I assume that y was a QR. So again, my Euler's criterion, this is just 1. Okay, and so that just gives me y. All right, so if I want to find the square root of a quadratic residue, my prime is congruent to 3 mod 4, then I just have to raise the quadratic residue to the p plus 1 over 4. All right, and I'm just going to kind of give another sort of random, no pun intended, application that I can use these square roots for before we start talking about the zero knowledge proofs. Okay. All right, and so the setup here, Alice and Bob, they want to flip a coin over the phone. Okay, so Alice is in Albuquerque, Bob's in Brussels. Greta Aunt Birgit has bequeathed them a car. They want to decide who gets the car. And Bob phones Alice and says he'll flip a coin. Alice chooses tails, and Bob says, sorry, the flip was heads, and Bob keeps the car. Okay, so Alice kind of suspects that Bob's being a little bit less than honest here, and talks to the local cryptographer to kind of come up with a plan of action for the next inheritance, whatever that may be. All right, so here's the protocol they come up with. And so Alice decides to choose a couple large primes, P and Q, that are different from each other, but both congruent to 3 mod 4. So Alice is going to compute the product of P and Q, send that to Bob. Okay. Bob is going to choose an x and z mod n star at random, so we can kind of think of this as the flip, and then computes y, which is x squared mod n, sends y to Alice. Okay. All right, so what Alice could do now, so y is a quadratic residue mod n. So that means that it's got to be a quadratic residue mod each of those primes, p and q. And Alice, since the primes are each congruent to 3 mod 4, then Alice could use the procedure on the previous slide to calculate all the square roots of y mod p, both the square roots of y mod p, both of the square roots of y mod q, and then recombine to find all the square roots of y mod n using the CRT. Okay. And of course, those square roots kind of naturally pair up. So we'll call them plus and minus a and plus and minus b. Okay. So one of those must be x, right? So x must be either plus or minus a or plus or minus b. And so Alice is going to choose one of those, say a, and sends that back to Bob. Okay. Or Alice is really calling dibs on both a and minus a. Okay. So she's going to either send a back or send the pair a minus a. It doesn't really matter. So that's the call. Okay. So if x was congruent to either plus or minus a, then Alice's call is correct. Alice wins the toss. Otherwise, Alice loses. Okay. So the question here then is, I guess, sort of the fundamental question is, what's to prevent Bob from cheating? Okay, so why can't Bob just say wrong? It wasn't plus or minus a, right? It was actually plus or minus b. Right. Well, the key is that Bob can't call plus or minus b without knowing what plus or minus b is, right? So if Bob says you're wrong, then Alice says prove that I'm wrong, and the way that Bob proves that Alice was wrong is to produce plus and minus b. Okay. The only way that Bob can produce plus or minus b, if those weren't the original flip, would be to be able to compute all the square roots of y. And the only way to be able to compute all the square roots of y is to actually know the factorization. Okay, so the point here is that Bob can't factor an arbitrary quadratic residue, even a quadratic residue that Bob himself produced. Right, so Bob can't find the square roots of an arbitrary quadratic residue without being able to factor in. Okay, so that's the safeguard here against cheating. Okay. All right, and so that kind of covers the first bullet point here. Right, so Alice can be sure Bob doesn't cheat if neither plus or minus a were Bob's flip, that Bob wouldn't be able to produce the other pair without being able to factor in. Okay. If Bob used plus or minus a to actually produce that quadratic residue, then Alice hasn't really sent any new information. Bob already knew that plus and minus a were square roots of y, and so therefore there's no new information that Bob would be able to use to try to factor in. Okay. Other things that may go wrong here. So Alice maybe tries to cheat by sending a random number other than the square root of y, but then Bob can easily check whether it's square root of y, so that won't fly. If Alice tried to set up something that was a product of 3 or more primes, well, in that case, then Alice would only be really decreasing her chances of winning, right? Because it would be harder for her to call the pair that Bob used to produce the quadratic residue, right? Because there, if it was 3 primes, there'd be 4 pairs of quadratic residues, and Alice would still have to call the right one. Okay. I guess Alice could try to send a single prime and cheat that way, but in that case, then Bob would probably want to run a primality test on the end, right, to make sure Alice wasn't cheating by just sending a single prime. Okay. Bob could intentionally lose. Okay, so that's a possibility here. So we have to. So this game has to be set up so that the only benefit to Bob is by winning as described by the protocol, right? So Bob could intentionally lose and say, yeah, the a minus a you sent me was the pair I used to generate the quadratic residue. Okay. And so that's, I think, pretty much the only flaw in the protocol that Bob could intentionally tank here. Okay, so here's a little example. So let's let n be 77, right? 77 is 7 times 11. So 2 distinct odd primes, each congruent to 3 mod 4. So suppose Bob randomly chooses x, which is going to be 58. Okay, so then Bob would compute 58 squared, which is 53 mod 57. Okay, so y would be 53 here. So that's what Bob would be sending to us. All right, and so what we could do then is say, all right, well, I'm going to look at 53 mod 7 first, right, which is 6, which is 4, rather. Okay. And so then the square roots of 4 mod 7 are clearly plus or minus 2. And then we want to look at 53 mod 11, which is 9. So the square roots of 9 are plus or minus 3 mod 11. Okay. And then I would recombine those to find all the solutions, right? So all the square roots of my original y. Mod 77. So for example, if I said z congruent to 2 and z congruent to -3 mod 11, and using the CRT, I would find the solution z equals 30 and its negation 47. Okay, so that would be one of my pairs. If I keep z congruent to 2 mod 7, but then take z congruent to 3 mod 11, I'll see z equals 58 as a solution, so I would take that and its negation, so 19 and 58. Okay, so I would call one of those pairs. If I call 19, 58, since Bob originally used 58, then I would win, right? So I called Bob's flip correctly. If I call 30, 47, send that to Bob, Bob could say no, the actual, whatever I call it, A or whatever I call it to generate the quadratic residue was 53. Okay, so you lose. All right, so this is a little aside on how we can use square roots. Okay. So the main topic that we're going to get into in our next unit are what are known as zero knowledge techniques. And so the idea here is that I want to prove something. Okay, so I either want to prove that I have some knowledge, I have some ability, prove my identity, so prove that I am who I claim to be. Okay, but I want to do so in such a way that I don't reveal any information to the party that I'm proving to, or reveal any information to a third party that may be eavesdropping. And so the idea here is, it's a good example of this is, maybe I want to take out money at an ATM. All right, so what do I do? So I insert my card and then I enter my PIN. Okay. But when I do that, then the ATM can harvest my card number and my PIN. Okay. And so potentially go and use that information to take money out of my account. Okay. So a better way, and then even if the bank is trustworthy, right? If somebody sets up a fake front on an ATM, then they could gather that information, right? And then maybe even communicate that information to the bank so that I can still take out my money, and so then they'll have my account number, my PIN, without me being any the wiser. Okay. So a better way of running things is to somehow, right, convince a verifier that that I know my account number, right, and I know my PIN, without actually revealing what those are. Okay, so we'd have more security if we could convince a verifier of some piece of knowledge, some ability, some identity, without actually revealing information. All right, and as usual, I like to kind of think of these things metaphorically before we jump into the mathematical implementations. Okay. So a non-mathematical version of this, so this is what's sometimes known as Alibaba's cave. All right, so we've got so two parties here. So now we've got Peggy and Vic. So Peg is the prover, Vic is the verifier. And so Peg is in an underground tunnel. And Vic is up here at the top. And so there's a locked door down here. And so Peg wants to prove to Vic that she could pass through the door. So she knows the combination to open the door, but she doesn't want Vic to know anything, basically. So not the combination, maybe not even whether she's able to pass both ways through the door or only one way. Okay. So the way we're going to do this, so instead of Vic entering the tunnel and watching what Peg does and thereby gathering that information, so Vic is going to stand at the top, and so Vic is not even going to observe Peg entering the tunnel. Okay. So Vic is just going to stand at the top, blindfolded until Peg's in the tunnel, and what Vic's going to do is going to call out a challenge each time. And the challenge is simply going to be left or right. Okay? So Vic is asking Peg to emerge either through the left side of the tunnel or the right side. Okay? All right, so so if Peg can pass through the door, then no problem. Right? So Peg just waits in the bottom of the tunnel, and so if Peg's on the left-hand side and Vic calls out left, then Peg just emerges through the left-hand side. If Vic calls out right, then Peg just goes through the door and then emerges through the right-hand side. Okay. I guess maybe we could suppose there's some ladders here for Peg to climb up as well. All right. On the other hand, right, if Peg can't actually pass through the door at all, then Peg may try to fool Vic. And Peg could probably fool Vic on maybe one or two passes, simply by entering through one side and then just hoping that Vic calls out the side that she entered through. Right. So if Peg is on the left and Vic calls out left, then she can emerge. Okay. If she's on the right and Vic calls out right, then she can emerge. But eventually she's going to guess wrong, right? Because she's only got a 50% chance of guessing correctly on each pass of this protocol. And so eventually, Vic's going to call right when she's on the left, and Peg won't be able to complete the challenge. Okay? Another interesting thing about this protocol is that so if Eve is watching the proceedings from Vic's point of view, right, she won't even really know if Peg can really pass through the door, right, because Vic and Peg could just be choreographing the protocol. Okay, so a third-party observer here gathers even less information than Vic. All right, some properties then that we want mathematical zero-knowledge proofs to have. So completeness, which means that if the statement is true, then an honest verifier will be convinced of this fact by an honest prover. Soundness, if the statement is false, then no cheating prover can convince the honest verifier that it's true. Okay? And then zero knowledge. Okay? So if the statement is true, then the verifier doesn't actually learn anything, right, from the protocol. Okay? All right, so we're going to look at a couple different versions of zero knowledge proofs. And so first we'll look at a discrete log-based version. Okay, and I'm going to do this one first because it's a little bit simpler, and then we'll look at a sort of integer factorization square root-based protocol in our next class. Okay. All right, so here's our discrete log-based version. Okay, so Peg is going to set up a secure instance of a DLP. So we'll have large prime P, primitive or otherwise large order alpha, secret A. So beta will be alpha to the A mod P. Okay, so Peg is going to publish P comma alpha comma beta. And Peg has set up this instance, so only Peg should know A. Okay, and of course, if challenged, then one thing Peg could do would be to confirm her identity by simply revealing A. But then the problem is then the scheme is not reusable, right? So we want, and also it reveals information. So that's precisely what we want to avoid, right? We want Peg to be able to confirm her identity without actually revealing it. All right, so here's the protocol. So Peg is going to choose a random K, right? And again, as usual, between 1 and P minus 1, and send to Victor R, which will be alpha to the K mod P. All right. Vic is going to issue one of two challenges. Okay. So the challenge can either just be R. Okay, so send back that same R. Okay. Or C could be beta times R inverse. Okay. All right, and so Peg then is going to respond, the correct response will be log base alpha of the challenge. Okay. So in the case that the challenge was R, and the response is just K, right? So log-based alpha of R is just K. In the case that the challenge was beta times R inverse, then the response is going to be A minus K, not B minus 1. Okay. All right, so in either case, no information is revealed. About it, right? Because in the first case, well, Peg just responds with K. What's K? Right? K is a random. It's just a randomly chosen exponent, right? Between 1 and P minus 1. Okay, so it's nothing to do with A. In the second case, A is here, but A is essentially masked by this randomly chosen exponents. Okay? All right, so we've got our first example of a zero knowledge proof. And so we can kind of think of this then as, right, Vic is sort of, we're asking which side of the tunnel Peg should emerge from. In the case that the challenge is R, we can think of that as being the left-hand side. In the case that the challenge is beta times R inverse, we can think of that as being the right-hand side. If Peg actually does not know A, then she won't be able to emerge from the right-hand side. She will be able to emerge from the left-hand side, but eventually she's going to be issued that challenge, which she can't respond to. So one interesting thing about this is that, so even if Peg doesn't know A, so doesn't know log base alpha beta, she can set things up so that she would be able to respond to the second challenge. Okay, so what? So one thing that we can note here is we can do the following. Okay, so there's a little trick that could be applied here. And that would be to generate R in the same way. Okay? But instead of sending R, send R times beta inverse initially. Okay. All right, so if that's the case, then notice the first challenge would just be R times beta inverse. Okay, but then the second challenge is R times beta inverse times beta, which is just R. Okay. So Peg could actually set things up. And so she could respond correctly to the second challenge, which would just be K, right? So the K that was used to generate the R. But then notice here, the correct response to the first challenge would then be K minus A mod P. Or mod P minus 1. Okay, which Peg cannot respond to without knowing K. Right? So essentially without knowing, this kind of sort of solidifies this tunnel metaphor, without knowing the correct A, Peg can advance, guess what the challenge will be, and if Peg thinks the challenge is just going to be the first challenge, then sending the correct R will work. If she thinks it's going to be the second challenge, she can send R times beta inverse instead of sending R. And as long as she can outguess Vic, she'll be able to fool him. But again, eventually, right, she'll guess incorrectly and won't be able to respond to the challenge. That Vic issues. All right, so next time we'll continue with zero knowledge proofs and see a protocol that is based on square roots.